Hey friends, welcome to the YouTube channel All About Electronics. So in the previous videos, we have seen that what is feedback amplifier, and we have also seen the different feedback topologies of the amplifier. Now in this type of amplifiers, since we are using the feedback, so it is also important to discuss the stability in these feedback amplifiers. So as we have discussed earlier, typically these feedback amplifiers are using the negative feedback. So here, this A is the open loop gain of the amplifier and this beta is the feedback factor. And if you see the closed loop gain of this feedback amplifier, then it can be given as A divided by this 1 plus A beta. So typically if you see, then this open loop gain of the amplifier is the function of the frequency. That means with the change in the frequency, the gain of the amplifier will also change. So in general, it can be represented as the A of S, and it shows that it is the function of the frequency. So as we have discussed earlier in these feedback amplifiers, typically this feedback network is the passive network. So here during our discussion, we will assume that this feedback network is the frequency independent. So we can say that here this beta is also frequency independent. So now if we replace this S by j omega, then this closed loop gain, that is x0 divided by xs, can be given by following expression. So here let's focus on this A beta term. So here, since it is a complex term, so it will have both magnitude and the phase. And at some frequency omega 1, it may happen that its magnitude will become 1 while its phase will become 180 degree. So basically it indicates that this term is the negative. Or in other words, now we will have the positive feedback in the circuit. And with these values, if we see the value of this term, then that is equal to minus 1. So due to that, now this denominator will become 0. Or in other words, the output of this feedback amplifier will become infinite. That means even if there is a very small input, then also we will get the infinite output. But if you see in the actual circuits, then the output cannot go beyond the biasing voltages. So in such conditions, we can say that a feedback amplifier is the unstable and it is not amplifying the input signal linearly. So the same thing can also be seen from the signal point of view. So let's say this is the input signal to the feedback amplifier, and let's say at some frequency omega 1, the phase shift of the A beta will become 180 degree. Or in other words, when this A beta is negative, then it means that the open loop gain of this amplifier is the negative. Because here we are assuming that this feedback network is the passive network and it is made up of only resistors. That means here this feedback network will not add any phase shift. That means the entire phase shift is added by this amplifier. That means here whenever we apply the input to this feedback amplifier, then this amplifier will amplify the input and it will also add the 180 degree phase shift to the input signal. So now this feedback network will send the fraction of the output signal back to the input side. And here at some frequency omega 1, since the magnitude of the A beta is equal to 1, so this feedback signal XF will have the same amplitude as the XS. But here due to the 180 degree phase shift, the signal will get inverted. So initially when we turn on the circuit, then there is no feedback in the circuit. Or in other words, this XF is equal to 0. So when we just turn on the circuit, then this Xi is equal to XS. And after the first iteration, this will be the feedback signal. So now this feedback signal will get subtracted from the source signal. So here, since the feedback signal is out of phase to the source signal, so after the subtraction, basically these two signals will get added. And due to that, now the input signal to the amplifier will have amplitude that is 2 times the source signal. So once again, this amplifier will amplify and invert this input signal. And once again, since the A beta is equal to 1, so the feedback signal which is coming back to the input side will have the same amplitude as the Xi. But this signal is 180 degree phase shifted. So once again, this feedback signal will get subtracted from the source signal. And due to that, now the amplitude of the input signal Xi will further increase. So now this amplifier will further amplify and invert this output signal. So in this way, with the each iteration, the output of the feedback amplifier will keep on increasing. And in this way, the amplifier output will go towards the instability. So the same concept is also used in the oscillators. But when we use this circuit as an amplifier, then this will lead to the instability. So as I said earlier, of course, the output of the amplifier cannot increase indefinitely, and eventually it will get restricted to the biasing voltage of the circuit. But still, because of this instability, we will not get the desired output. So this condition arises when this A beta is greater than or equal to 1 and this phase shift is equal to plus minus 180 degree. But on the other hand, if this A beta is less than 1, then even if the phase shift is 180 degree, then also this term will be less than 1, and hence the denominator will be non-zero. So of course, since the denominator is less than 1, so the output will also increase. But eventually, it will get settled to some finite voltage, and hence, in this case, we will not face the issue of the instability. So we can say that the issue of the instability will arise whenever this A beta is greater than or equal to 1 and this phase shift is equal to 180 degree. That means we should avoid this condition in the feedback amplifiers. So in the actual feedback amplifiers, to check the stability, we should focus on this term A beta, where the A is the open loop gain of the feedback amplifier and the beta is the feedback factor. And here, this A is the function of the S, or in other words, the A is the function of the frequency. So let's say, for some feedback amplifier, we are getting this type of expression for the A beta. So the question is, from this expression, how do we find the stability of the amplifier? So there are a couple of ways to find the stability, and one of the ways is using the Bode plot. So when we discuss the control system in detail, then we will learn about this Bode plot in more detail. But here, from the feedback amplifier perspective, let us learn some basics of the Bode plot, and let us learn, using this Bode plot, how to check the stability of any closed loop system. So if you see any Bode plot, then in any Bode plot, we are drawing the two plots, that is magnitude and the phase plot. So while plotting the magnitude plot in a transfer function, or in this case in this expression of the A beta, when we have some constant amplitude, then on the logarithmic scale it can be represented as 20 log k, and on the magnitude plot it can be represented as the constant value. So until we encounter any pole or zero in the expression, this amplitude will remain constant. So in this expression of the A beta, at some frequency omega 1, if we encounter the 0, then from this frequency onwards, the amplitude will increase at the rate of 20 dB per decade. On the other hand, if we encounter the pole at the omega 1, then after this omega 1 frequency, the amplitude of the plot will reduce at the rate of 20 dB per decade. That means we can say that the slope of this plot is equal to minus 20 dB per decade. On the other hand, in the expression of the A beta, if we have a pole at the origin, then from omega is equal to 1 onwards, as we go forward, then the amplitude will reduce at the rate of 20 dB per decade. And at this omega is equal to 1, the amplitude will be equal to 0 dB. And similarly, if we have a simple 0 at the origin, then as we go forward from omega is equal to 1, then the magnitude of the plot will increase at the rate of 20 dB per decade. And at this omega is equal to 1, this magnitude will be equal to 0 dB. That means below this omega is equal to 1, if we see the magnitude of the plot, then that is equal to negative. On the other hand, in the expression of the A beta, if we have a multiple poles at the specific frequency, for example, the two poles at the frequency omega 1, then from omega 1 onwards, this magnitude plot will reduce at the rate of 40 dB per decade. That means if we have a simple pole at the specific frequency, then the magnitude will reduce at the 20 dB per decade. But on the other hand, if we have a two poles, then this amplitude will reduce at the rate of 40 dB per decade. And similarly, suppose we have a three poles at the omega 1, then in that case, from omega 1 onwards, this amplitude will reduce at the rate of 60 dB per decade. That means with the each pole, this amplitude will reduce at the rate of 20 dB per decade. And the same is the case for the multiple zeros. That means for example, if we have two zeros at the specific frequency omega 1, then from omega 1 onwards, this amplitude will increase at the rate of 40 dB per decade. So this is how, based on the expression of the A beta, we can plot this magnitude plot. So similarly, now let us see how to draw the phase plot. So for this phase plot, in the expression of the A beta, if we have a constant value, then this phase shift is equal to 0. Similarly, if we have a 0 at the origin, then from the beginning, the phase shift will be equal to plus 90 degree. Likewise, if we have a pole at the origin, then the phase shift of the plot will be equal to minus 90 degree. But on the other hand, if you have a pole at the specific frequency omega 1, then let us see how this phase changes. So at low frequencies up to 0.1 omega 1, we can assume that the phase is almost 0. And from that point onwards, the phase starts reducing. And as you can see, it will reach to the minus 90 degree at the 10 omega 1. And at omega 1, if we see the phase shift, then that is equal to minus 45 degree. So that is how the phase changes with the single pole. That means the single pole will add the phase shift of the minus 90 degree. And this phase shift will occur at the frequency which is 10 times the pole frequency. That means if the first pole will occur at the omega 1 frequency, then at the 10 omega 1, the phase shift of the plot will be equal to minus 90 degree. And at this pole frequency omega 1, this phase shift will be equal to minus 45 degree. So that is how the phase changes when we have the single pole. And later on, we will see that how this phase changes when we have a more than one pole in the denominator. So in this way, for any given transfer function, we can draw this Bode plot by drawing this magnitude and the phase plot. So now let us see from this Bode plot how we can find the stability of the feedback amplifier. And for that, let us take one simple example. So let's say this A beta is equal to 100 divided by this S plus 50. So as you can see, here we have some constant value K, and in the denominator we have a one pole. So before plotting the magnitude plot, first let us represent this function in the standard format. So for that, if we take the 50 outside, then in the numerator we will have this 100 divided by 50, that is equal to 2, and in the denominator we will have this 1 plus s divided by 50. So here, now if you see the constant term, then that is equal to 2, and in the decibel that is equal to 20 log 2, that is equal to 6 dB. So if you see the magnitude plot, then it will start from the 6 dB and it will remain constant up to this 50 radian per second, because here the first pole is arising at this frequency. So from that point onwards, if we see the slope, then that will be equal to minus 20 dB per decade. So that is the magnitude plot for the given expression. But as you know, this Bode plot is incomplete without the phase plot. So now let us see the corresponding phase plot. So as you can see from the expression, here we have the no zeros. That means initially the phase shift will be equal to 0 and the first pole will occur at the 50 radian per second. So up to 0.1 omega 1, or in this case up to 5 radian per second, we can assume that the phase shift is equal to 0, and from there onwards the phase will start reducing. So it will reach to the minus 90 degree at the 10 omega 1, or in this case it will reach to approximately minus 90 degree at the 500 radian per second, and the phase shift at the 50 radian per second will be equal to minus 45 degree. So here from 0.1 omega 1 to 10 omega 1 we have drawn the constant line. But if you see the actual plot, then it will look something like this. So as you can see, in this one pole system, the maximum phase that we are getting is the minus 90 degree. And since it is less than 180 degree, so we can say that the first order systems are inherently stable. That means the feedback amplifiers, where the expression of the A beta has only one pole, are inherently stable. So similarly, now let us see what happens when we have the two poles. So let's say the expression of the A beta can be given by the following expression. So as you can see, now we have a two poles at the omega p1 and the omega p2. So first, let us see the magnitude plot. So here, due to this constant k, initially we will have the fixed amplitude that is equal to 20 log k. So up to this frequency omega p1, this amplitude will remain same. And after that, since we are encountering the first pole, so the amplitude will start reducing at the rate of 20 dB per decade. That means this slope will be equal to minus 20 dB per decade. And at the omega p2, since we are encountering the second pole, so this slope will further reduce by the 20 dB per decade. That means now, if we see this slope, then that is equal to minus 40 dB per decade. So here, at some frequency omega x, this slope will cross the horizontal axis. That means at this frequency omega x, this amplitude will become 0 dB. Or we can say that this amplitude will become 1. Alright, so similarly, now let us see the phase plot. So as you can see from the plot, here we do not have any zeros, but here we have the two poles. So initially, the phase shift will be equal to 0. And from point 1 omega p1 onwards, the phase will start reducing. And it will reach to the minus 45 degree at the omega p1. And as we have discussed earlier, at the frequency of around 10 omega p1, this phase shift will be close to minus 90 degree. So up to 0.1 omega p2, this phase shift will remain constant. And after that, it will further starts reducing. So as you can see, it will reach to the minus 135 degree at the omega p2. And further, at the 10 times omega p2 frequency, the phase shift will be close to around minus 180 degree. So here, between 0.1 omega p1 to 10 omega p1, we have drawn the straight line. And further, between 0.1 omega p2 to 10 omega p2, once again, we have drawn the straight line. But actually if you see the phase plot, then it will look something like this. So here also, if you see at the very high frequencies, the phase of the A beta is close to minus 180 degree. But actually, the phase will reach to the minus 180 degree at the infinite frequency. So we can say that for the two pole systems, this feedback amplifier will be on the verge of the instability at the very high frequencies. But still, we cannot say it is the unstable. But as we go from the two pole system to the three pole system, then there are chances for the instability. So let us see that. So let's say this is the expression of the A beta. So as you can see, now we have the three poles at the omega p1, omega p2 and the omega p3. And in the numerator, there is some constant magnitude k. So first of all, let us see the magnitude plot. So here, due to some constant value k, we will have some finite value up to the omega p1. And at omega p1, since we are encountering the first pole, so the amplitude will start reducing at the rate of 20 dB per decade. Likewise, the slope will change further at the omega p2. And from omega p2 onwards, the slope will become minus 40 dB per decade. And once again, the slope will change at the omega p3. And further, now it will reduce by the 20 dB per decade. That means if we see this slope, then that is equal to minus 60 dB per decade. So that is the amplitude plot. And similarly, now let us see the phase plot. So if we see the phase plot, then it will look like this. So here, up to 0.1 omega p1, the phase will be almost 0. And from 0.1 omega p1 onwards, the phase will start reducing. So at omega p1, it will be close to minus 45 degree and it will reach to the minus 90 degree at the 10 omega p1. So from 10 omega p1, if we further move ahead, then once again it will start reducing and it will reach to the minus 135 degree at the omega p2. And at the 10 times omega p2, it will reach to the minus 180 degree. So further if we go ahead, then the phase will further reduce and at the omega p3, it will become minus 225 degree. And at the 10 times omega p3, it will be close to minus 270 degree. That means if we see the phase plot, then it will look like this. So now, if we see the magnitude plot, then the frequency at which this gain crosses the horizontal axis, or when the gain becomes 0 dB, is known as the gain crossover frequency. So for stability, what we need to see is that at this gain crossover frequency, the phase of the A beta should be greater than minus 180 degree. So in this case, if you see, then it is very close to minus 270 degree. That means it is already less than minus 180 degree, and therefore it indicates the instability. Because if you see the condition for the stability, then for a stable response at the particular frequency, this A beta should be less than 1 when the phase reaches the minus 180 degree. So in this case, if you see, when the phase reaches the minus 180 degree, at that time, this A beta is greater than 1. And therefore, the issue of the instability will occur. So here in the phase plot, the frequency at which this phase reaches the minus 180 degree is known as the phase crossover frequency. That means for the stability, the gain crossover frequency of the feedback amplifier should be less than the phase crossover frequency. Because if this condition is followed, then at the phase crossover frequency, if we see the magnitude of the A beta, then it will be less than 1. So in these feedback amplifiers, or in general in any feedback system, the stability of the system is measured in terms of the phase margin. So with the help of this phase margin, it is possible to find out how stable is the amplifier. So in the next video, we will discuss the concept of the phase margin from the feedback amplifier perspective. Moreover, we will also see some compensation techniques using which it is possible to improve the phase margin of the feedback amplifier. And in this way, it is possible to make the feedback amplifier more stable. But I hope in this video, you understood using this Bode plot how it is possible to find the stability of any feedback amplifier. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.